Hello again, everybody, and welcome to this last video of the semester on the last part of applications called optimization. So what is optimization? Actually, it stems from a very basic principles. So what's the main idea? If you have, for example, I don't know, a curve that models your profit. This is the way the profit actually goes. So you may have like a y-axis and an x-axis where suppose that x represents the number of gizmos that you produce. I like the word gizmo. And this is the profit you can actually make by making so many gizmos. So let be the profit, let it be in dollars. Okay, the idea is actually fairly simple. What we would like to have is if the curve looks like this, big if, right? If the curve looks like this, well, we would like to be as much as possible here. We would like to be where the profit, the y value, is the highest, right? Now that corresponds to, as we all know, a local maximum. And a local maximum is a point where the tangent line is 0. That is where the derivative actually is. Well, it's not the best tangent line I have ever drawn. We can make it a little bit thicker and cheat a little bit. But you get the idea. So if we can actually find a point on the curve where the tangent line has a slope of 0, this is where f prime at some point C is 0, and we can find where that point C is, then we will have the level at which our production should function in order to maximize our profit. So as you can see, the idea is very simple. So we have a curve and we try to actually figure out what the right curve should be for the problem in question. This is part of the modelization we'll have to do. And basically now we find the critical numbers, we find where the maximum is or the minimum, depending on what you're looking for. And basically you proceed, you solve the problem. So let me show you an example. Oh, actually, perhaps before the example, I should probably, let's go this way. Let's do the method and then we'll illustrate. So methodology. So what is going to be the method that we actually use for optimization? I like it to give it to you in terms of like steps. So step 1, very important. People neglect step 1 and it's always a mistake. Identify clearly your variables. Identify your variables. Now in most problems, you're going to have to be dealing with a maximum of 2 variables. It's pretty rare we go beyond that, at least in this course. Also, here, if it's useful, draw a picture if needed. So some problems require you to actually have some sort of a visualization of what's going to happen. So drawing a picture helps you figure out what is it that you want and where the variables go. Not all problems will actually require a picture, but many of them will. Step 2, using the variables in step 1. So you see, like everything is going to stem from the first step. Using the variables in step 1, decide on the function, I guess is probably the best way to say it. Decide on the function you want to either minimize or maximize. So you want to minimize a function. For example, you want to minimize your cost, you want to minimize if if you own a fleet of trucks, you want to minimize perhaps the time they spend on the road. If you own airplanes, you want to minimize perhaps the fuel that they use, whatever, or maximize. That, of course, can be applied to revenue, profit, yield of any sort. So you have some variables you found in step one. You look at the problem, you say, okay, this problem is about maximizing profit. So you say, okay, I want to maximize my profit, but I need to express this in terms of the x's and the y's, whatever that I have in step one. So step three, again, using the variables in step one, find an equation. Again, using the variables in step one, find an equation. An equation, so keyword in here, find an equation that links the variables together. So an equation that will have all of the variables in the same equation. That's what I mean. That links all the variables together. Okay, good. We're on our way to the solution to this. So what have we done? We selected variables. We know what is it we want to minimize and maximizing. We have an equation here that will link the variables together. Oh, I forgot a little something here. Before, let's go to step 4. Put in bracket, isolate one of the variables. Isolate, doesn't really matter which one. If you have x and y, it could be either one. But you should try to isolate one of the variables. So if you have x and y, at the end of this step, you'll have y is equal to blah, blah, blah in terms of x. Or x is equal to blah, blah, blah in terms of y. It's up to you. Okay, good. Step 4. Essentially, step 4 is replace in what you have in step 2. Replace in step 2. So replace in the function you want to minimize the outcome of step 3. What is the outcome of step 3? The equation with a variable isolated that represents the link of all the variables together. The outcome of step 3. We now should have a function with only one variable. A function with only one variable. This is important because in the next step, we're going to find where the local min and the local max are. So all of these is to actually figure out an equation in one variable that corresponds to what you want to minimize or maximize. The actual calculus work takes place here in step 5. Derive the function in step 4. Derive the function you have obtained in step 4. Find its critical numbers. Make a table of variation to find the local either max or min, depending on what you're looking for in your problem. Make a table of variation to find the local min, and that's it. You're done. The problem is solved. So you conclude with a sentence saying, Well, I should be producing 500 gizmos in order to maximize my profit. Let's see how we can actually formalize this language in an applied problem. So before I erased, 5 steps. You follow these steps very rigorously and you will be successful solving these problems. Variables. Some sort of a function that says, okay, I want to maximize profit, I want to minimize cost, whatever. An equation that links together the x's and the y's. At the end of that, you'll have y is equal to something. Replace this y is equal to something back into the function in step 2. That's what we do in step 4. At the end of this step, we have a function of one variable. And in step 5, we do the calculus, we derive, find the critical numbers, and you know the rest. Okay, let's illustrate. Let's see if we can work out a couple of examples that would show how the method works. All right, well, here's a classic problem. So example 1, this is a problem for the ages, probably the best introductory problem in optimization. A farmer has 2,000 meters of fence and wants to use it to enclose a rectangular plot of land and wants to use it to enclose a rectangular, so keyword, I'm going to put it in capital, a rectangular plot of land on his farm. Say. All right. One of the sides, just to make the problem more appealing, one of the sides of the rectangle is located by a river and does not need any fence. It's kind of a natural, the river is a natural barrier, and does not need any fence. Okay, so we have a big roll of fence. If I unroll this big roll, I'll have like 2,000 meters. That's huge, obviously, 2 kilometers worth. And basically what I want to do is I want to form a rectangle with this fence, with one side actually not requiring any fence because it's by a river. So question, find the dimensions, find the dimensions of the plot that will maximize the area. That will maximize the area of the plot of land that he wants to enclose, obviously. All right, so there's clearly some keywords in there. We will dissect this before we erase it, but before that, I'd like to show you some of the possibilities that exist. So basically, what could happen? What could happen? Well, here's an example of what could happen. You could actually go, all right, so here's my river, and I could actually go for that. I could actually go for a very, very, very long and narrow plot of land like this. So that's all of my 2,000 meters of fence. So let's say I have here, I don't know, I have here 800 and 800 and oh, let's go larger than that. Let's go 900, 900 and 200 to complete this. so it's much longer than it is wide. Notice that these are meters, and if you add them all up, you have 2,000, right? So basically, what is the area of that? What is the area of this? Area is equal to, well, it's a rectangle, right? So base times height, pretty easy. Base times height, so that's 180,000 square meters, 200 times 900. So I could totally do this and it would work perfectly well. I could also do this. I could also do something quite the opposite. I could actually have something that is relatively narrow and much longer, like that, right? So maybe I give the dimensions here, I don't know, like 100, 100, and I have here, no, actually, that would be 1800, so a total of 2000, and that would actually be even narrower than this, although it's not to scale. What would be the area of this new plot of land? That actually makes me use, as you can tell, the sum of the sides is actually 2000. This time around, what do I have? I have here, again, 18 times this. I have 180,000 square meters. So you can get the same area, basically, by playing around with these numbers. Here's one last example. You could actually have something, here's my river again, river. You could have something perhaps like a little bit more like this. And maybe this is 800, and this is 600, and this is 600. Again, if you sum it up, you're going to get 2,000. So what is the area of this one now? Well, base times height, this times this, so that is 400 and, whoa, yeah, here you go. That actually is a much larger area. So what I'm trying to say here is that you can play around, do some trial and error with these guys, and it's not going to be obvious what comes out to be the best way of doing it if you want the largest possible area. From this elementary trial and error, these are not very good. This last one is much better. But is it the absolute best we can do? That's the question that calculus will help us answer. Okay, so much for the intro. Let us actually go step by step over the method used to solve this problem. All right. So, step one, I guess we could here draw a little bit of a picture, and it would help us figure out what the variables are going to be. So, picture, so no fence along the water, and the plot of land is going to be like this. Now, since I don't really know what measurements will give me the largest area, I'm clearly going to call this X and going to call this Y. And I'm going to say, for the sake of completeness, let X be the width of, that's a T, the width of the plot, and Y be the length of the plot, both in meters. So I have an X, and I have a Y, and I have a picture. So that's pretty simple, step one. So step two, what is it that I am trying to maximize? Well, I erased the problem, lack of space, but if we read the problem again, the last sentence will say, find the dimensions of the plot of land that will maximize the area. So I'm going to say maximize the total area, which means now I have to express this in terms of the variables that we have in step one. What is the area of this rectangle? Well, length times width, base times height, x times y. They do. That's all we do. Good enough. Step 3. Now we need to find an equation. Now we need to find an equation that brings together the variables. An equation that brings together the variables. A little hint, that step actually must include the only part of the problem we haven't used so far. The numerical element given in the problem that we haven't used is what? Is how much fence we have, right? We have 2,000 meters of fence. Haven't used that yet anywhere. Now it's time to use it right here. So I'm going to put some fencing here, I'm going to put some fencing here, I'm going to put some fencing there. So this plus this plus this is all the fencing that I am going to use. Wouldn't it make sense to say x plus y plus x? So x plus y plus x, that's all the fencing that I need, and it's all the fencing that I have. So shouldn't it make sense to say x plus y plus x is equal to 2,000? That is to say, 2x plus y is equal to 2,000. That is to say, remember that at the end of this, we'd like to isolate one of the variables. The easiest variable to isolate is clearly y. So what we have here is a pretty simple y is equal to minus 2x plus 2,000. All right. So that's an important step. We now have a nice equation that involves both of the variables that we put in step 1. And now for the step 4, sorry. What are we doing? Step 4? Well, replace what we got in step 3, right back what we got in step 2. So step 2 is maximize x times y. So now it's going to become maximize x times y. And in this y, I will actually replace what I have in step 3. That's what I'm saying. Take step 3, put it into step 2. And what you're supposed to have at the end of this is a function that has only one variable. So here we go. That gives us an f of x that is equal to minus 2x squared plus 2,000x. Great. We're doing fine. Finally, a little bit of calculus here in step 5. We figure out the prime of this function. So we figure out the prime of minus 2x squared plus 2,000x. And what do we get? We get minus 4x plus 2,000. I am now looking for the critical numbers of this function. So since there is no denominator, I don't have to worry about this. I'll make it equal to 0 and solve. So minus 4x is equal to minus 2,000. It appears that x is 500. Now, this is a critical number. I don't know yet if it's a local min or a local max. So I'm going to make a very quick little table there, very simple, nothing fancy, just for the f prime and df. I'm not going to start this as minus infinity because this is a real life problem. You cannot have minus 100 meters of fence. So I'm going to start it at 0. Going to go to infinity. Going to put in my only critical number, 500. And then I'm going to take a number here, say, I don't know, 1, and I'm going to put it here, and I'm going to find that it is positive. And say here I put 501, I'm going to find that it's negative, so that the function goes up and the function goes down. And I get quite exactly what I was hoping for. I get a local maximum. And I have found the answer to the problem. Now it's just a matter of concluding. So the dimensions should be the dimensions should be, to get the maximum possible area, 500 equal to x my width. Hold on. I can do better than this. I can reverse that and say that the width equals 500 meters and the length equals to, I don't know, where do I go to find the length? Yeah, step 3, the equation that actually links the variables together. So we have that x is 500, yeah. So put it back here, minus 2 times 500 is a minus 1,000. Minus 1,000 plus 2,000, so here you go. What is this saying is that if you do it this way, if you build your rectangle so that this is 500 and this is 1,000 and this is 500, you will actually have, they didn't ask for it, but we'll put it down anyway, you actually will get an area of this times that. So that's 500,000 square meters. What we're saying here in this problem is that you can't beat this. No matter how you do trial and error on these guys, you can never beat that value. This is the largest area that we can come up with. It can't be larger than that. So that's an example of how one of these problems can be solved. If I have the time, I would like to take a quick look at perhaps something that is a little bit more economics oriented. So example 2. Example 2. So this time, I'd like to talk about a little bit of functions that we have seen before in the marginal analysis, so cost and profit and things like this. So suppose that a company has a cost function. So suppose that the cost function of a company, cost function of a certain company is given by C of x is equal to half x squared plus 40x minus 31, where x is the number of, again, for lack of better words, gizmos made. All right, so you're given the cost function, half x squared plus 40x minus 31, and suppose also that the selling price is regulated, nice word, by the equation P of x. What shall we have as a P of x? We could have something like okay. This, ladies and gentlemen, is something in economics that appears very often. It is known as a demand function, basically, right? So this is a demand equation. Not like extraordinarily important for us, but in Cal 2, we're going to play a lot with demand equations and supply equations. But we're in Cal 1, so we're just going to say the price depends on the number of items that one actually produces. All right, so basically, what can I do with all this? What question can I ask? I got a cost, I got a price, so standard question. Find the production level. Find the production level. What does that mean, production level? It means how many items we should produce, we should make. How many items we should make, obviously. So find the production level for which the profit is maximum. All right, so. Here we go. Last question of this video. Keyword, clearly, yes, I want my profit to be maximum. So keep that in mind. It'll come up when we do the steps. Step 1, I don't think I need a picture here. I don't have a field to cover with fence or anything like that, but I should identify my variables. How many variables are there? Well, if I look at the structure of the problem, there is X, and that's it. X is the number of gizmos that I make. So that's my production level. So only one variable here, not two. X, number of items or gizmos made. All right, pretty simple. Step 2. What is it that I am trying to minimize or maximize? Well, I'm trying to maximize my profit. Aha! Now, do you remember profit from marginal analysis? Profit is always given by revenue, not revenue, revenue minus cost. Okay, let's leave it like that for now. Okay, step 3. Step 3, I'm supposed to find here an equation that links all the things together. Well, that's pretty obvious, I guess. So profit is, do you remember how we calculate revenue? Revenue is price multiplied by quantity. So I'm going to put that in a bracket. This is my revenue minus my cost. So price, what is price? They give me price. Price is 120 minus a half x. So 120 minus a half x multiplied by the quantity. Well, the quantity is x. That's the number of gizmos that we make. Minus my cost. Well, they give me my cost. So half x squared minus 40x minus 31, right? Okay, good. So what shall I do here? What shall I do here? Well, I will certainly multiply these guys in, and I will get 120x minus half of x squared, and I'll bring the negative inside this bracket, minus half of x squared minus 40x plus 31. Let's go over here, and I get that my profit is, when I'm going to collect my like terms, minus a half x squared minus a half x squared is minus x squared. 120 minus 40, that's plus 80x. And where is my constant? It is here, plus 31. And you can see here that at the end of step 3, I don't really need to go to step 4 in this problem, because we don't have two variables, we only have one. So there is no back substitution of putting one variable back into some sort of a function. Everything here is self-contained in this profit equation. So I can actually go to step 5 right away. Perhaps I do this over here, since we don't really need the statement of the problem anymore, and I don't want to cram this into like a small little corner of this very small whiteboard. So step 5, my profit function is equal to minus x squared plus 80x plus 31. Good. So profit prime, we shall derive and find the critical number. That means that this is minus 2x plus 80. Finding the critical number is easy. You make it equal to 0. And you solve this. Minus 2x is minus 80. So divide by 2. And apparently, if we make 40 gizmos, we are going to get a local something. Is it a local min? Is it a local max? Well, let's make a quick little table. I guess I can squeeze it in. And the table goes like this. So again, 0, infinity, and my only critical number is 40. Here's an f and an f prime. If I take 0, I'm going to get that in here. I'm going to get a plus. And if I take 50, that number is too big. It's going to be a minus. So that goes up and that goes down. And yes, we have found a local maximum. So the answer to the question is conclusion. Conclusion, the company should make 40 gizmos to maximize its profit. The company should make 40 gizmos to maximize its profit. And that's how this is done. So I hope that you found this useful. We are going to go to class later on this week. We're going to work out more problems that involve this economic structure of price, cost, and revenue. So be there. And in the meantime, I wish you well. Ciao.